Hello everyone and welcome back to this next lecture in the machines lecture series, and this is where we had left off in the last lecture where we had written down the ratings of the motor, especially the manufacturer specifications that can be found on the machine nameplate in any machine motor, or rather any motor that can be found either commercially or even in a laboratory. Every motor will have a machine plate which will contain some of these readings. So now that we have these ratings and we've started translating what is physically on a motor into a simulation model, in this lecture we will continue and start using these ratings to build, or rather to calculate, the parameters of the equivalent circuit of the induction motor. And for that I can show you this particular spreadsheet. This is what we're going to do. This is the equivalent circuit of the single phase induction motor, and we're going to use these parameters and gradually calculate all these parameters of the equivalent circuit using the ratings of the motor. So as before, if you're interested in these kind of video lectures, but you would like something a little more comprehensive, I do have full-length online courses that you can find on my website, which is pythonpowerelectronics.com. So you just have to click on the button Learn, which will take you to the list of courses. So the very first course I have is Simulating Power Electronics Circuits using Python, and in this I talk about how you can use Python and Python Power Electronics to simulate power electronic circuits. The second course I have is Basics of Digital Signal Processing for Power Engineers, and in this I talk about how you can use Python and Python packages like the SciPy packages and the signal package within the SciPy package to design and analyze filters for power engineering applications. The third course I have is called Simulation Magnetics for Power Electronics using Python, and in this I talk about how you can use Python and Python Power Electronics to model magnetic components like inductors, coupled inductors, and transformers. The fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and the Python control package to analyze and design controllers for power engineering applications. And the last course I have is a free course called Why Specialize in Power Electronics. This is a motivational course which is designed for either junior undergraduates or high school students who want to choose their specialization as they go further. And this is to tell you about some of the challenges and opportunities available in power electronics. So the link for this page is provided in the description for this video. If you're interested, please do check it out. So with this, let me return back to the simulation. So as I already said, these are the motor ratings. Now I'm going to split this into two parts, which is the manufacturer specifications and computed ratings. That is what we can compute using either documentation or using experiments. So for example, the rated voltage, the output power are provided by the manufacturer. But the rated efficiency at rated power and the input power are not provided by the manufacturer. You will either have to consult the documentation or you would have to perform an experiment. Right? So therefore, these are computed ratings. The next is the synchronous speed. The synchronous speed is usually not provided by the manufacturer. The manufacturer will provide the number of poles and the rated frequency. The synchronous speed we'll have to calculate. So therefore, I will split this up so that we know that these are ratings that you can find on any machine. So you just have to go to the machine, read these ratings from the nameplate of the machine. And these are what we can compute using either assumptions or by referring to the documentation. So now that we have this, we are going to start with the no-load test. That is, we are going to use the no-load test. So as said before, the no-load test involves running the motor with the rotor at no load. So no mechanical load is connected to the rotor, which means that the slip is very close to zero because the speed of the rotor when the motor is at no load is very close to the synchronous speed, and therefore the slip is close to zero. Because the slip is close to zero, this parallel branch is almost open circuited, is assumed to be open circuited, which means the rated voltage is applied purely across this parallel branch. That is the resistor that represents the core losses and the inductance that represents the magnetizing inductance. Right? And we can ignore these two values as well because at no load current there will be almost no drop across these two components. So usually in a no load test When we do so, we are going to measure the power that is absorbed by the stator, and we're going to measure the current flowing in the stator. So these two are known, right? We know the no load current and we know the no load power. If you have a machine and you have access to a laboratory, you can go ahead and perform this test, right? However, in our case, I'm going to assume these values. So let me write here no load test. So the no load test will have two values, and I'm just going to write this P no load, that is the power absorbed, or rather the power that is drawn by the motor at no load, and we can say I no load, that is, this is the current that flows in the stator at no load, right? These are usually can be measured or can be assumed, and in the assumption I'm going to talk about another assumption as well. So the P no load can be assumed for a motor between around 1 to 3% of the rated input power, right? This is an assumption. You can change this to be around 4-5% as well, but then you're talking about a slightly lossy motor. So ideally speaking, you would choose, I'm going to write this down in a comment, that no load losses rather, are 1 to 3% of the rated input power. So which means that we can choose this to be around, let's say I will choose this to be 2% of P in rated, right? And this is an assumption, a fair assumption. So as already stated, at no load, the losses are the magnetic losses, which means this is the losses in the core losses, the hysteresis losses, and the eddy current losses, right? And these are usually not very significant. Now, the I load we can measure. So this I load, let me go back to the circuit. This I load is the current that flows in these parallel branches. That is the current that flows in this branch with the resistor that represents the core losses, and the current that flows in the magnetizing inductance. The sum of these two currents will be the no load current. Alright. Now, for now, I'm going to assume that I don't need this, and I'll tell you why. But first, let us use this no load power. So now the no load power, if we know the no load power, we know that the no load power is only due to this lossy, or rather this resistance that represents the core losses. And as I said, because the current is negligible, we can neglect these two components as well. So the rated voltage comes directly across this core loss component. So what that means is RC is equal to V rated multiplied by V rated divided by P no load, right? This is a simple computation, that is V squared over R. Now the next point is, what about the no load current? If we want to be absolutely rigorous, and if you're performing an actual test, then in that case this current is the sum of these two. That is, it's the sum of RC and LM. We already have calculated RC. That means all we need to do is calculate LM. So we have the current, we have the voltage, as well as we have this RC. So therefore calculating LM is fairly simple from these two equations. But since this is a simulation model and we are only estimating and assuming parameters, we can make a further assumption. So here the assumption we make is that the magnetizing current for a motor is between 2 to 5% of the rated current. Right? Now in a transformer, this magnetizing current is between 1 to 2% of the rated current. For a motor it's larger because a motor has an air gap. Because there is an air gap, the reluctance to the magnetic path is usually much higher, because of which the magnetizing current will also be a little higher. Right? Now, what this means is I need the rated current. So now for the rated current, we are going to make another bit of assumption. Now P in rated, we already have P in rated. So P in rated is usually VI cos phi, where cos phi is the power factor of the motor. We know the rated input power. We know the rated voltage. So to be able to calculate the rated current, I need the power factor at the rated output or rated power. So what that means is I can say PF rated, that is this entire cos phi, is equal to, I'll say 0.8. I'll call it 0.8. You can choose 0.85, 86, 88. If you check out any induction motor textbook, you'll see a vast number of values being chosen. Now that we have this, we can just calculate I rated as V rated, or rather P in rated, P in rated divided by V rated multiplied by PF rated. This is just this equation. So now I have the rated current. I have made some assumptions. I have made the assumption that the efficiency, we know the efficiency at rated conditions, due to which we have the rated input power, and we know the power factor rated conditions, due to which we know the rated current. Right? And these are fair estimates. Now that we have this, I'm going to calculate I magnetizing, I'm going to call this I mag, as 0.05 times I rated. Right? So this is 5% of the rated current that is drawn by a motor when it is working to supply rated mechanical output power. Right? This is a fair assumption. Now, as I said before, I'm making an assumption because this makes our life easier. You can calculate it rigorously by choosing a no load current and by using this value of RC and VSRC to calculate LM. You can, but since this is a simulation model, this is much easier. And as you can see, once you have IMAG is nothing but omega, or rather 2 into, let me just write the equation, math.pi. Actually, I have not imported math, so let me go up and import math, because I'll need math anyway, and multiplied by F rated, that was a mistake, F rated multiplied by LM. So this is the reactance. This is the reactance of the magnetizing inductance. This reactance is basically V rated divided by IMAG. And therefore, quite obviously, all I have to do is take this term down and I have my value of LM. So, as you can see, with these few assumptions, I have been able to calculate the value of RC, which is the resistance that represents the core loss of the machine, and the magnetizing inductance, which is responsible for producing the flux in the air gap. Right? This is what I have computed using the no load test. So I have used the manufacturer ratings, made some further computations, made some further assumptions, and then made computations, and use the no load test and further assumptions to be able to calculate two parameters, which is RC and LM. So we now have four parameters left. We have the stator resistance, we have the stator leakage inductance, we have the rotor resistance inductance, and we have the rotor resistance. Now these four parameters will be calculated by the blocked rotor test. But we have performed one stage, which is calculating the core loss resistance and the magnetizing inductance. And that is what we have done in this lecture. So now in the next lecture, we will continue and use the blocked rotor test to calculate the remaining parameters. So with this, we are getting one step closer and closer towards building the simulation model for our induction motor. With this, I'm going to end this lecture. If you have any doubts, send me an email or message me on social media, whichever is your preference. Otherwise, I will see you next week where we will continue with this blocked rotor test. Thank you so much for watching and see you soon. Goodbye for now.